So this is the damage that was on the card when it came in. First part of the video is fully dedicated to the repair process. This is the fast forward of the work once all the broken traces had been fixed up. I had to confirm that they're functional. Once we figured that out, that it's all rolled out and connected, I applied some curing mask to the card to prevent disconnection while the card is being worked on. Checked for shorts, everything was good. We connected it to SD protocol, but unfortunately it came up with the card being locked and we couldn't read it directly through the interface. So the only way that we could get the data from this device is by going after the NAND protocol, which is what you see me do right now. There are a bunch of signals that need to be hardwired to a breakout adapter to establish this NAND protocol connection, but once we actually get there, the device will be able to provide us with a physical image that is located inside of the NAND. With that physical image, later we'll be able to perform different data conversions and apply them within the software to bring us to the actual data. So let's see how this case unravels, guys, and hopefully we get it. This is a 30 in 30 challenge I'm doing. Every day I post a video for 30 days straight, and we'll see how far we can go. Hopefully I can keep up and we'll get the entire challenge finished up without hiccups. So enjoy the show, guys. Let me know if you have any questions in the description box, and I'll answer every one of you, and hopefully we'll be back for more tomorrow. Now all that's left is power and ground, so 1, 2, 3, 4 power. 1, 2, 3, 4, 5, 6. This is what we're looking like. I mean, I'm happy with how it turned out. Let's test it. We're open. We're gonna need to start a new task. Let's get the idea of this thing. We can see here that we're getting the ID. 98 is a Toshiba. Wow, D1 is also connected to the wrong place. Alright, so I graphed them all out. So D1 was in the wrong place. It was up here. Had to switch it down. D0 is where it needs to be. And the last signal that was in the wrong place, the wrong time. Okay, now I've checked them all. And finally, we have this beautiful ID come out, and let's go into parameters, flash chip parameters, basic microchip parameters. We have 16 gigs, which is perfect. That's what the size of our chip is. Everything is in good position, so we only have one CE signal. Time to read it. Have a look at the direct mode real quick. Page designer, bit view. Some rough XOR going on. Okay, this is what the data looks like. This is XOR, this is data. No shifts, perfect, we can read it. The only problem here is that the service area is encrypted. Oh no, it's right there. Okay, good, so we can do this. This looks like a FISON controller. Amazing. Let's clear this first. Clear. Read chip. Let's go. 5 megabytes per second. Memory chips had been read. This looks really good. I'll close this up and find error correction codes. So go ECC auto detection, and quickly it finds it. We're gonna run it and get it done. So the error correction is done. If we build a map of this stuff here, and create a submap of all of the invalid sectors that didn't get corrected, we only have 15 megabytes left. So let's set this up for readout and select them, maybe go like, I don't know, 50 tries on stock basic settings, see if we can get some improvement on it. Beautiful. That's excellent. So if we look at the map now and create another map of invalid sectors, we have nothing here. So the whole thing is perfectly cleaned out and ready for assembly. So as far as the elements of the mix go, I think we got it. So once we remove the mix from our transformation graph, we ended up with something that is a little bit saddening for the night. The fact that this device did not consist of one part is becoming pretty evident to me. If we look at this line of elements and we go into service information for selection, just to make sure that there is interleave involved, we can scroll down and we see that service area looks quite similar. So we're good here. This is how it's supposed to look like with interleave applied. I ran raw recovery on the bottom section and came up with nothing but exFAT file structures, which means that there is no data that is found that exists on its own. So my only guess is that there has got to be another part involved, and another part collaborates with part that we have right now. It's very similar to the Stripe CE. So we will end up with very brief bursts of data being merged across all four parts. I guess that's what accumulates the speed of the device, but again, without having that part, we can't complete the recovery even on partial level at this point, because it's very similar to recovering content from like a striped RAID when one of the drives is dead and not accessible. The block size is just too small to have any data fit inside of it to be valid for recovery using only one part. So we need to look for that second part. Okay, so I think I found what the issue was. The way that PC3000 is set up by default to figure out how many banks are involved, it's going to read until the ID is no longer the same as it showed up originally. So if we have C0 connected, C1 disconnected, but C2 connected again, it's gonna show that our device only has one C channel. It's not gonna show the second part that may be linked up to C2. So in order to prevent that from happening, I'm going to read ID, but we're going to put this checkbox here. Do not interrupt in case of chip ID reading error. So what it's going to do, it's going to give us the first bank, it's going to give us second bank not found, third bank found, fourth bank not found, and so on and so forth. So now it actually discovered 2. And the same way that we had it, if we were only checking for it the first time, would probably be okay. To read the second half, I'm going to use this solderless adapter. So the card goes in, just push down on it, and slide the cover down. Okay, configuration is set up. This is the beauty about these adapters, is that everything can be configured and everything can be manually set up. So from the schematic, we know that our device locates C0 and C2. It doesn't detect C1, so it throws an error. For that reason, what we're going to have to do is go on the default setting here, disable these. Okay, so we're going to disable C signals altogether, just leave C0 in place. Now over here we have a pinout, and we have pinout from the reader, pinout from the microSD. We're going to use FF wire. Select C2 and wire it up to CE1. Is that right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now our C1 signal is here. This one is disabled because this is default and this is custom. So we're going to delete chip information once again, and now when we ID it, we can have that actually disabled because it's going to read first and the second right away. At least it should. Now we have 2 banks. And this one we can load from file, and this one we can start reading. Read it from here. Let's have a look at it in direct mode just to make sure that we actually get some sort of data that is different. So let's go into Page Designer on our extracted copy first that's been corrected. Let's pick sector, copy it, and gonna get a snip tool, set this aside, and go into this one, Page Designer, I didn't copy it. So Page Designer, let's go that was it. Copy, Page Designer, paste, So this is what 2 copies look like. They don't look the same, and they look pretty good to me. So let's go and explore this segment. Very clean, no shifts at the end, perfect. Set out to read. Now we gotta wait once again. So after quite a bit of back and forth, I'm finally here correcting the last bit. If we go into the map of our part 3, create submap for invalid sectors, we have very small amount that we're gonna reread right now, and with read retry we're gonna probably pick them all up on the first run even. Perfect. These 2 belong to the first channel, these 2 belong to the second channel. Let's add XOR element, because we've determined that there is XOR involved on the first run. And it's this one. It comes with a transformation for the pages. First part of the first channel mixes with the first part of the second channel. I'm going to go ahead and synchronize the channels. So by the time we're done with the mix, this is what the transformation graph ends up looking like. This is a fairly complicated controller, Phison 8210. One of the characteristics that it has, it's this element for synchronization of the channels. And one of the benefits of PC3000 Flash is its support for 8210 translator feature that it can provide. That's what allows the tool to build cards like this with a file system. In our case, ability to build a translator to get the results that we need would have been absolutely crucial, because without translator we wouldn't be able to get this file structure by block number assembly, and since most of this content on this card is MP4 files, all of that stuff would have been scrambled. But with the translator we're able to get full file structure, and everything about the files ties up pretty well. So this is ready for delivery. As always, guys, if you have any questions, drop them in the comments below. If you have a card or a flash drive or any other type of digital media device that needs work, check us out in the description box. Links to contact us are there. And if you're new to the channel, subscribe. Thank you guys for watching, and I'll see you all in the next episode.